Hello everyone. Here's an introduction to the concept of digital manufacturing. Digital manufacturing in our engineering design project, students need to integrate 3D modeling, numerical analysis, and digital manufacturing. For these emerging technology application abilities, we have arranged related learning content in our engineering design process. For the topic of digital manufacturing, we've chosen an appropriate development plan based on the predictive analysis of our 3D model, applying digital manufacturing methods to manufacture our design prototype and then use this prototype to do some testing and evaluation. With this digital manufacturing method, we can obtain our prototype more conveniently and faster. Therefore, students should seize this opportunity to make good use of modeling, analysis, and manufacturing integration concepts to actually manufacture the compressed air racing car in our engineering design project and complete the subsequent testing and evaluation. After improving upon some shortcomings, we will complete the theme that our engineering design course will have arranged for students to learn and make. In the following structural diagram, digital manufacturing integrates digital modeling tools, including the 3D modeling, which we learned in the previous phase. Another modeling method is by using a 3D scanner to reversely obtain the digital data of a pre-existing design through a 3D scanning method. After the modeling is completed, the model needs to be manufactured later, which can be done through subtractive or additive type of machinery. For digital manufacturing output, the concept of subtractive manufacturing is that for an existing material, which can be a block or a plate, and through cutting methods, we cut out the shape from the existing material. This concept is a subtractive method. There are several types of this kind of machinery. The first one is the vinyl cutter, which usually cuts the thin films of material, such as cutting sheet, paper, or cloth materials. The second one is Cnc Milling. We will provide students with relevant operation methods and application cases about this machine in subsequent design and production. The third one is the laser cutting machine. In the past, students may have come into contact with it in our Living Technology course. In our engineering design project, many materials can be cut into the shapes that we want through the laser cutting machine and assembled into our compressed air racing car for related design applications. The second type of digital manufacturing machine uses the additive method. This type of machine stacks layers upon layers, such as our 3D printer, using the additive method to stack up layers of materials. This concept is called additive processing. The most commonly used machine is the 3D printer. In the following course, we will also frequently use the 3D printer as the equipment for our prototype output, which will be used in the project production of our compressed air racing car. Therefore, digital manufacturing tools can assist our project production and provide great convenience in prototype production. Previously, in the Living Technology courses Robotics Project, Product Design Project, and Mechanism Design Project. For the design production of many complex and high-precision products, we used digital manufacturing tools to ensure a smooth progress in the production project. This is especially true for repetitive mass production. The digital manufacturing tool works like a personal factory, which can produce many products we need through this process. These are examples of using the laser cutter to make tires needed for our compressed air racing cars. In this design and production, regarding the laser cutter's precision, especially for the case of roundness and perpendicularity of the cut, as well as the optical correction, we will further learn about its correct operation so that the quality and precision of our work can meet our needs. The second digital manufacturing machine that we will widely use and learn about is the 3D printer. For the operation of this machine, we will learn the production of hollow model with high span, using simple supports to make our printing faster. The second production method is used when our printing size is not big enough and we need to make large-sized models. We can do bonding using an ultrasonic knife so that our model can be printed in sections and then assembled to make a large-sized model, such as the compressed air racing car. The third machine that students can learn and experience is the CNC milling machine. In past courses, students may have had less opportunities to use the CNC milling machine. In our compressed air racing car production project, the CNC milling machine's cutting speed can finish the prototype production of our model relatively faster than 3D printing. Through the technical application of turnover milling, students can machine from the top view direction as well as the compressed air racing car's side contour lines. This is a small 3D printer. When printing our compressed air racing car, we need to segment the model, print them in sections, and then assemble together. This is a common approach for the production of large-sized models using the 3D printer. Here is a picture of students using the ultrasonic knife to repair the 3D model. In the following operation demonstration, the teacher will also demonstrate how to use the ultrasonic knife for the students to observe and learn. Here are two pictures of how we made the wheel bearings for the 3D printed car body of our compressed air racing car. The top picture shows how we used nuts as the bearing for our axles. The bottom picture shows commercially available bearings aimed in our 3D model. Students can use these two methods as reference in the upcoming production process. Students may be able to get better performance for their compressed air racing car. For the 3D printed models, we can use paste fillers or liquid fillers such as cement paint to make the surface of our model smoother, so that it can offer better performance for the subsequent drag testing. For this part's operation, we will show a demonstration in upcoming videos. There are also many manufacturing difficulties and dead angles, as well as subsequent processing and machining with CNC milling. The teacher will also give a brief demonstration and operation instructions in upcoming videos. Hello everyone, here is a demonstration of how to output the 3D model with the 3D printer once the 3D modeling is finished. The screen shows a finalized tire for our compressed air racing car. Before exporting the tire, we usually place the largest surface area flat on the working plane, which is the side of the tire that we see on the screen. Here we'll use the gumball to rotate the tire 90 degrees, and the tire will be flat on the working plane. At the same time, in order to improve the 3D printing efficiency, since the compressed air racing car has 4 tires, here we will use the copy feature of the gumball. We press and hold the Alt key, then click and hold the red arrow. You can copy the model into 2 by moving it. We'll repeat the operation here. We'll select both tires at the same time, press and hold the Alt key, then click and hold the green arrow and drag it backwards. This way, we have copied the 4 tires needed for the compressed air racing car. After selecting our models, we go to Files, Export Selected. For the file format, we'll choose the STL, Stereolithography format. Generally, we suggest using English or numbers to name the file so that there is less chance of error occurring during 3D printing. The tolerance setting of the file must be less than the 3D printer's minimum tolerance, which is usually 0.02 for most printers, so here we set it to 0.01. After exporting the file, we open the 3D printer's slicing software. We'll select our 3D printer and import the file. Next, we will start up the printer. Next, we'll click on Setup. We will replace a new material into the 3D printer. Once we see that the new material is replacing old material and changing colors, it is when the replacing of materials is complete. Before printing the model, we'll select Automatic Placement, confirm that the model is flat on the working plane, then select the printing function, which means 3D printing, the filling method, which refers to the printing density. Once selected the printing density, we output the model's code that our controller needs for operation through software algorithms. You can see on the screen, the 3D printer's slicing software has output to the printer the base needed for printing as well as the program code for the layers shown on the screen. To operate the 3D printer, we first need to make sure that the base is really adhered to the 3D printer's base plate. If it is possible to be around during the printing process, we should always pay attention to whether there is enough material to complete the printing and whether the operation is normal. If the 3D printer's base plate is designed to be removable, then we opt for removing the base plate first and then take out the model so as to avoid damage to the machine caused by improper force. Finally, we use a scraper to remove the model from the base plate and remove the base to complete the printing of the model. Here is a demonstration of the CNC milling operation procedure. First, we open the cutter parameter setup window. To set up the cutter diameter and relevant milling parameters. Next, we'll place the model at the machining point of origin. We'll set the milling range to 200 times 80 millimeters. We'll adjust the model below the cutting range to allow the cutter to work within the correct range. Next, we'll set up the model's rough milling path. We'll set up to horizontal milling and perform the initial cutting. After setting up, we'll run a simulation program for the initial cutting to make sure that there is no bumping during the cutting process. Next, we'll set up lateral cutting in the direction of the x-axis. We'll also run a simulation program to check if the lateral cutting process will be successfully completed. Next, we will convert the cutting path into control code. We will place the foam block into the CNC milling machine. We'll fix it in place and start the machine and return to the material's point of origin. Here we'll use a dynamic way to adjust the height of the cutter. In order to avoid hitting the cutter, we'll start the cutter axle and adjust the height of the z-axis while it is rotating. We'll set this height as the point of origin of the material. Next, we will start the CNC. This is our normal cutting speed, which will cut the model's shape to the correct shape at once. There are still many dead angles with CNC milling which cannot be processed. Here we'll use some post-processing machine techniques to make our prototype smoother. First, we'll use a drill press to cut out the round hole needed for our high-pressure cylinder. We'll use a 90-degree wood block to keep the car body perpendicular to the drill press after adjusting to the proper height. hold our material and wood block. We'll slowly and steadily cut out the hole needed for the high-pressure cylinder. At the same time, we need to lift up the cutter frequently to remove the scraps for a smoother machining and prevent blockage of the hole. Let's switch to the hole saw. To cut out the hollow space needed for the tires and allow them to rotate freely within the car body. We'll adjust the height of the table and also adjust the milling nut to the depth we need. So that later on, the drilling depth of the holes can be consistent. Carefully and steadily, we'll align it to the position of the holes that need drilling, holding the material steadily and drill down the holes. Because we adjusted the drilling depth, we can achieve the same drilling depth for each tire. Next, we'll use a band saw to cut the edges that were not cut with the CNC machine, as well as the bevel angles needed for our model. Here we use a belt sander machine to perform the initial polishing. When polishing, we need to gently contact the material with the belt sander while also moving it fast to remove the scraps, which is the correct way of operation. Next, we'll use a box cutter with the foam's easily breakable feature to cut out the space for the tires. At the same time, the box cutter can also cut out some of the shapes that we need. Next, we will mark the space needed for the axle rotation on the surface of the model. Here we'll use a framing square to keep the left and right side of the axle parallel to each other. Here, we use the method of cutting towards the center, cutting inwards from different angles so that our small arc can be cut out smoothly. Here we'll use a sandpaper to polish the tooling lines on the model. This method needs to be done fast and with a light touch to produce a smooth and continuous surface on the model.